In this section, I'd like to keep teaching the Bessel's functions. When the nu is integers, Bessel's functions j sub nu and j sub negative nu are not independent because, as I show in the practice, j sub minus I is equal to the minus 1 to the i's times j sub I. So to express the general solution of Bessel equations, the y equals c sub 1 j sub nu x plus c sub 2 j sub negative nu x. We cannot express general solution using the j sub minus nu because these two functions are not independent, because this is the equation to relate the two functions. So we have to create independent functions. The independent functions called the Bessel's functions of the second kind. Second kind expressed y sub nu. Y sub nu is defined using the j sub nu and j sub negative nu's. Using cosine nu pi times j sub nu x minus j sub minus nu x over sine nu pi. This is a definition of a Bessel function of the second kind. J sub nu and y sub nu are independent, so we can express a general solution of Bessel's equations using the j sub nu and y sub nu is y equals c sub 1 j sub nu plus c sub 2 y sub nu. Then you might be interested in the graph of the y sub nu as a function of x when the nu is 0, 1, 2, 3, and 4. So you can easily recognize the Bessel function of the second kind is approaching the negative infinities when the x approaching to the 0. When the x becomes larger, you can find the oscillational behavior of the Bessel function of the second kind. So we can use a Bessel function of the first kind and second kind to create general solutions of Bessel equations. Maybe it might be beneficial for students to study the parametric Bessel equations. Parametric Bessel equation is defined these equations. So the difference is alpha squares x squares appears in the equations. Then we'd like to change the independent variable of x to the t using the t equal alpha x. So t equal alpha x. Derivative of y with respect to x, y prime is equal to dy dx. Then we can apply the chain rule, dy dt, dt dx. Then alpha t is defined alpha times x. So derivative of t with respect to x becomes alpha. So it becomes alpha dy dt. y2 primes is expressed d dx, dy dx. Then you can substitute these expressions here. So d dx alpha dy dt. Then you can apply the chain rule. d dt alpha dy dt dt dx. So this becomes alpha. So alpha squares second derivative of y with respect to t. Then differential equations. We have x squares y2 prime plus xy prime plus alpha square x squares minus nu squares y equals 0. y2 primes, you can substitute these ones. So x squares alpha squares the second derivative of y with respect to t. This is x alpha dy dt plus alpha square x square minus nu square y equals 0. Then we can express the t equal alpha x. Then this becomes t squares dy second derivative of y with respect to t plus t dy dt plus t squares minus nu squares y equals 0. This is the original Bessel equations. So solutions of the Bessel equations is expressed as c sub 1 j sub nu t. Now independent variable is t plus c sub 2 y sub nu t. Then we could substitute t equal alpha x. Then solution is expressed c sub 1 j nu alpha x plus c sub 2 y sub nu alpha x. When you find out this differential equations, parametric Bessel's equations, very similar to the original Bessel equations except the alpha square x squares. Then solution is expressed with the Bessel functions. Just difference is the j sub nu alpha x and the y sub nu alpha x. You need to replace the x to the alpha x. Okay, this is the end of the sessions to learn Bessel function.